Our first talk will be by Nick Lanning, who just finished his PhD defense, graduating in December. Yeah. And he'll tell us about his work he did during his PhD.
Thanks. So if you looked at the quote page, like on Tulane's website, you notice that it said quantum information and related, in parentheses, topics. So this is one of the maybe only and related topics. But the reason it's relevant is because, here at LSU, this has been a theory project for the past 5 years. So we've developed this toolbox of things we can do with spatial modes. And it stands to kind of bridge the gap in between what we can do here at LSU from a quantum information perspective, and then all the way to what can be done experimentally, like, for example, at Tulane. So I'll give an overview of kind of everything we've done, but focus on the quantum side of things, because this is quilt, not kilt. That would be something different. So I'll just throw up some of the publications we've had so far and kind of talk through an overview, and then you can jot down any of these groups if you want to look. So the project began as a collaboration with the College of William and Mary group, which is this first paper at the bottom. And what they were trying to do is just describe the optical depth dependence of squeezed vacuum generation. So squeezed vacuum, just vacuum, quantum vacuum, optical vacuum with suppressed quantum noise. And they just wanted to describe, what's happening as the optical depth changes. So a medium, in particular, this was a Ford mixing scheme with rubidium vapor, so making the atomic vapor denser or making the medium longer, and seeing how that affects the noise suppression. So they began just by verifying, okay, we're sending in ideal laser beam. It was prepped by single mode fiber, so it's a LG00 mode, and what should be coming out should also be that ideal laser beam. So we'll do some beam traces and just check that it is. Well, it wasn't. So this kind of opened up this whole avenue, or this whole area of research, where we wanted to describe the spatial multimode structure of this squeezed light. So we described that mainly experimentally in this first paper, but we started to develop this corresponding theory. And we'll talk about that a little bit in the following papers. And the second experimental paper is where we kind of went full circle. As we started to understand what was going on with these transverse spatial modes, we could actually really begin to understand how the squeezed vacuum will change with the optical depth, because it very much depends on the spatial mode structure of the input beam, where that beam is focused inside the nonlinearity, the length of the cell, all these things. So we really had no hope of understanding the optical depth scenario until we started to understand the spatial mode structure. So we had always intended to have like standalone theory papers, and the interaction with the nonlinearity theory grew to where it needed to be a classical paper and then a quantum paper. And while I was working on the interaction with the nonlinearity, Jahal was working on the interaction with spatial masks. Because in these two papers, we investigated the beam diffusion using spatial masks in kind of a beam tracing scenario. Like bring an iris in around the beam and move it around a focus after you've created the squeezed vacuum, and see how the noise changes. So you also need a quantum theory of how the quantum noise is going to interact with the spatial mask. So these are all published. And then we also have the corresponding classical theory of diffraction using spatial modes. So this is in contrast to typical diffraction theory, where we have like the Fresnel regime, the Fraunhofer regime, near field and far field, and this kind of gray area in between where you have to use, be careful with your diffraction theory. Well, it turns out that you can just use a spatial mode decomposition, and it works wherever you are. So this one has been submitted. We also started investigating some OAM transfer things in Fourier mixing. So this is a different Fourier mixing process. It's related to intensity squeezing, which is being done at Tulane, or has been done at Tulane. And we're also investigating, kind of transitioning from this, investigating in context of squeezed vacuum to entanglement. Because what we've learned is typically if you're trying to enhance your noise suppression, or you want to develop a resource that you can use for metrology or something, it typically requires that you're going to simplify the mode structure or tailor it in some way. And then if you want to increase the entanglement or the conductivity of the state, then it means you might want to make the mode structure more complicated. So those two contrasting ways to look at it, and this last paper is going to focus on that. So that gives the big picture. So today what I'll do is I'll talk about the semiclassical theory just a little bit, just touch on like a little quantum optics intro, and then really go into the quantum side of the theory. So this is the intro to the LG modes, the transverse-spatial modes. So if any point anybody has any questions, please stop me. But we probably have some people in the room that are very, very familiar, and then some that, like me 4 or 5 years ago, had no idea. We started with this project at the College William & Mary, and we sat down, looked at each other, and said, "What's an LG mode?" You know, like, so it was all very new, but these days it's very commonplace at least to me. So the LG modes, these transverse spatial modes, and these intensity patterns that we have here are just the profile of the beam, like if you were to shine it on a screen. And they're solutions to the Praxial wave equation here, which is it's just an approximation to the Helmholtz equation, where we say the beam is not going to change very much in Z. So you have like this, you still see that the operator is squared here, but in Z it's not. So what this means is you're going to find solutions that behave like a beam, and they don't change very much in Z, Z being the propagation axis. But they're indexed by these two indices, L and P. L is the azimuthal index, and P is the radial index. And I have the whole equation here. What really all I want to do is point out that it has an overall Gaussian profile. The Laguerre polynomials show up, and then it has this phi phase with L and this other long phase known as the GUI phase. So as the P index changes, it's hard to see here, but you just get more and more rings. As the azimuthal L index changes, you have this donut mode that gets larger and larger, and this corresponds to orbital angular momentum in the beam, which also increments as you go up. And then you can have superpositions thereof, for example, 1 and -2, so you can have 3 lobes, 2 and -3, you have 5 lobes. And then if you throw in P into the mix, then you still have that lobe structure, but more and more rings.
Orbital angular momentum in the beam, a classical description, orbital angular momentum of what?
So if you're thinking about it classically, you would say that the face front of the beam has this vortex structure.
The polarization state. So
Well, it's not polarization, no. So it's the, you could have spin angular momentum, right? Well, this is just a different type of angular momentum, the orbital angular momentum in the beam, and it's this vortex structure. So L = 1 would mean you have this one rotation per wavelength, and then 2 would be 2. So as L increments, you get this more intense phase structure. And the way you think about it, how this beam would interact with matter, the spin angular momentum would make like a particle spin. But they've shown that if you have a particle or something suspended and you shine it with this beam, instead of just spinning, it would go like this. So it travels with that vortex phase front. But this also corresponds to LH bar per photon. So that's how the two correspond classically in quantum. And some other buzzwords would be the Rayleigh range here. So it's the distance that the waist grows by √2. It's a way we understand properties of the beam. And I don't have the equation here, but there's a relationship between the waist and the Rayleigh range. It has to do with the wavelength of the beam.
Are these far field diffractions? interaction patterns, near field, where are they taken?
Well, these are plotted at the focus.
To the far field.
We'll just, yeah, I mean, yeah, they're plotted at the focus here. And depending on the superposition of modes you have, as these interesting phase terms, you can have the intensity pattern kind of be strange near the focus, but typically away from the focus, it settles into what it's going to be, then it just grows. So what we want to do is understand what's going to happen if I send, the simplest case, just a mode that's been prepped by the single mode 005, so an ideal laser beam. What's going to happen if I send that into a nonlinearity? The output being, what is that structure going to look like? And then to complicate it, well, what if I send like a beam like this? So that's the idea, to predict what the output mode structure is going to look like. So the semi-classical theory, we approach it, but all we want to do is solve the inhomogeneous paraxial wave equation. So in general, if you're thinking about a nonlinearity, you're going to derive some polarization that is going to be a complicated function of the field over here. So I've already done it here. You see that instead of writing E here, I have E naught. So we make a Born-like approximation and just plug in the form of the input field, which in this case, we're basically treating the right-hand side like the source of the new mode structure. And this is a good approximation, even better than the Born approximation for the Schrodinger equation, because really the nonlinearities in many cases are behaving like a source. Like you had vacuum inputs, and then on the other side of nonlinearity, you have new beams. So it really is behaving like a source. So when you do this, what we did was develop a Green's function approach to allow us to predict the output mode structure, and it just boils down to this nice simple form where this is like for a squeeze vacuum case where we don't need to have an attenuation factor or anything like that. But basically we just have this new mode structure with an amplitude, and this amplitude that we integrate over Z here is just basically the mode overlapping inside the nonlinearity. And this is an example from or the figure is from our OAM transfer paper, and this data along the right side is taken from this paper here at the bottom. So this really stretches the theory. I guess you could say as far as you could go, because or it stretches the Born approximation, because in this case it's not a pump beam and a probe beam. It's actually just two pump beams that we have here, and then a response at a long wavelength, so this is like 5 microns, and then the conjugate beam at 420 nanometers. So within the scope of the theory, we typically talk about, okay, we had a pump, we have a probe, how are we going to describe the conjugate beam that comes out? But in this case, it was all spontaneous. So we had to figure out a way to simulate this interaction. So we have this basic just setup of the problem, and then the energy diagram. So we have two pump photons that are annihilated, then we have the signal and conjugate that are created, and we want to predict the mode structure of this beam here. And in the experiment that they conducted, they never detect this beam because they don't have good detectors at 5 microns. So I won't go into too much more detail, just to say that we use the theory, we simulate this interaction, and we actually found much better agreement than what they had in their paper. So of course they plotted their data, and they also had a theory to predict the mode structure, to say, okay, yes, this is what we expect, but we have a much better thing. You can see by this is the one I can reach, so I'll say this one. We have this darker and lighter lobes. So this is just to show that the theory is working really well, and there would have been naysayers to say, well, this is just a Born approximation. It's not going to work well for other regimes like this. Well, it actually does work really well. So this is just a bit of a quantum optics intro. So I said squeeze vacuum, and what we mean by squeezed vacuum is it's just noise, vacuum fluctuations that have suppressed quantum noise. So the prototypical problem that you start off in with quantum optics is just to quantize the harmonic oscillator, which is, we see in regular undergrad quantum optics course. And this is the Hamiltonian of the quantum harmonic oscillator up here. But the point I want to get at is that basically we have these energy eigenstates of the harmonic oscillator, and they turn out to be these number states. And I really just want to get at how we visualize those in phase space. So the number states have a precise photon number, so that's why it's portrayed here as this ring. So we know precisely how many photons we have, but we don't know any phase information. And the other interesting part is that the expectation of the electric field for the number states is 0. So that's a very non-classical state. And the other interesting part is that, okay, even when I have no photons, I still have these fluctuations in the field, the so-called vacuum fluctuations, which are one of the hallmarks of quantum optics. So the next step when you're going through your quantum optics course is that, okay, well, how do we recover our idea of the electric field? And we do that with the coherent states, which are these states which are the eigenstates of the annihilation operator. So blah, blah, blah. The point is that we actually recover our idea of what the electric field is, this sinusoidal nature. And again, what's nice about them is that they have the same noise as the number states. So you can just imagine that, okay, as n goes to 0, we're left with these fluctuations, so it's just a blob at the origin, and then a coherent state is a displaced vacuum state. We keep that same amount of noise. But the other thing you can do is squeeze that noise, and that's what the squeeze state is. What we have. So there's a squeezing operator, and basically it's operator that corresponds to evolution in a nonlinearity. And what this does is that blob, this circle that would have been in the origin, it gets squeezed and it can be oriented in some strange direction in phase space. Why we're interested about this is because it can be used as a resource in quantum metrology, quantum information, other things. So this is just the single mode case, right? We were thinking about a single mode of the quantum harmonic oscillator. Now we're stepping into this transverse-spatial mode. So we want to predict how the squeezing is kind of dispersed through all the spatial modes. Couldn't find the right word. But that's basically what we want to do. We want to extend the theory from the single mode theory to a multi-mode theory and predict how the squeezing is going to be in all these transverse spatial modes. So, to do so, we follow the same prescription that you would find in a quantum optics text, except, like I said, we want to keep track of all the spatial modes. So this is just a depiction of the interaction at the top. We're not really going to care about the pump beams. We're basically going to make a parametric approximation. So we drop the operator character of the pump. But what we really want to know is we have these vacuum inputs. What are these modes at the output and how are they correlated? So to do so, we can write down the Hamiltonian like this on the left. And we want to keep track of all the possible mode structure in A and B. So A and B are two distinct modes going into, spatial modes going into a nonlinearity, but in each one there can be all these transverse spatial modes. So in this beam, there could be a combination of all that mode structure that I showed before. So we keep this potential mode structure. We can put that in the Hamiltonian, and it makes for something very cumbersome and hard to do calculations with. So the idea is just to write all those spatial modes that are in A and all the spatial modes in B, write them as this vector, and then write this corresponding amplitude matrix, which allows us to do, which allows for a little bit easier calculation. So all this corresponds into being able to write a squeezer, very similar to what you would see in a quantum optics textbook, except, like I said, these are vectors, and this is, instead of just being the squeezing number C, it's a squeezing matrix C. We can find the corresponding Vogel-Leibov transformations of how the modes transform. So now we know with these vacuum inputs, we know how A and B behave. They behave like this, with R being, let's say, basically a left polar decomposition of C. So if C was just a complex number, you could write it as R e to the half theta. So now R becomes this matrix, and then theta is also a matrix. But it shows how, this is basically how all the modes are mixing. So that's all fine and dandy. But what are we actually going to do with it? So we can calculate lots of interesting things. We can calculate the quadrature, variance and covariance matrices. We can investigate how the photons are distributed amongst all these modes, and cook up ways to investigate how the modes are coupling in the interaction. And in this case, this is an analogy to two-mode squeeze vacuum, right? So I keep sticking my arms out like this. What we're talking about is, you pump it could be a crystal, I guess. We can tweak the theory. A crystal or a atomic vapor with a laser, and then you have these two output beams. And you want to know the correlations between these two output beams. And in these two output beams, you have all the transverse-spatial modes. So on top of that, you want to know the correlations between all the transverse-spatial modes. The L over here is talking to the L over here in what way? The P mode over here is talking to some other different P mode over here in what way? And that's what the theory is telling us. And we define the quadratures in this way because it's correlations between the A and the B. So that's the last. Next to last, theory page or equations page. The other thing to say is that there's also this notion of an ideal basis to look at the squeezing, and those are known as the eigenmodes of squeezing. Basically what you want to do is just you take your squeezing matrix, you can diagonalize that matrix, and then each of those eigenvalues corresponds to a collection of modes that has a certain amount of squeezing. So you look at your largest eigenvalue and you say, okay, this corresponds to this collection of modes, and that collection of modes has the best squeezing out of this whole collection. And it's nice because whereas before the modes transformed with those Vogel-Leibov transformations that had the matrices, now it's simplified. So these are just the canonical two-mode squeeze vacuum equations with the matrices have disappeared. Okay. So I'll transition into several examples, and then we'll be done for the day, or I'll take some questions. So
Not done for the day.
you can all go home. I'll be there. So whenever I was cooking up this theory, the whole point, or the whole time, my inspiration was, okay, fine, we can do some calculations, but I really wanted to be able to depict the correlations in a way that you can immediately kind of see what's going on and find ways to tailor it. So I'll show several of these matrices. So this is the covariance matrix, then we'll go on to talk about the coupling matrix as well. And since this theory can treat any general four-way mixing scheme, it's kind of like a Swiss Army knife. You might not need the toothpick or the tweezer or the saw and everything. So this is like the simplest case we can do. Just some four-way mixing scheme that's actually just single mode squeezing. So in this case, you have these pump photon annihilated. You have this photon created in a different polarization mode. So this is like Y polarization and X polarization. So in this case, you don't need the two A and B modes. It's basically just one mode. And so the point here is that, okay, take that B, you set it to A, and you lose all the crosstalk. So this is the variance along the diagonal. And then as you make the interaction more complicated, okay, well, if I allow for P crosstalk in these interactions, then you can have covariance off diagonal. And then we'll go to the next case, something like this, where it's a 2-photon resonance scheme, where in this case, even if these carry no OAM, this could excite some OAM. So you could have a negative L here, a positive L here, and not violate OAM conservation, and that's what's on this next screen. So this is like saying, okay, I can respond at 1 in one arm if I respond at -1 in the other arm, or I can respond in -1 and then 1 at the other arm. So -1 and 1. So this is just showing the correlation in these modes, in the covariance. Probably have just a couple of minutes. So another thing we can do is analyze how we can funnel the photons that we're creating in these nonlinear areas to specific modes. And that's what this is doing here. This is the pump waste and the waste that you're going to collect after the nonlinearity. And the question being asked here is, how do I get most of the photons to go to the 0, 0 mode? Like if we're pumping with just an ideal laser, how do we get the photons to go into that particular mode again? And it's when you pick the waste to be, in this area, in this dark region. So this is just another way to analyze what beam parameters we should pick. And this is a spontaneous parametric down-conversion scheme where we use those parameters that we investigated to begin with. And I'll just jump to another way that we analyze the interaction. And this is that interaction strength matrix that was up at the bottom of one of the other plots. So it just shows us that as we expected and as we model, that most of the interaction is going to be with the 0 in the 0, 0 mode. Well, no matter, even with this optimized situation, we still have response in the other modes. How much?
2 or 3 minutes, 2 minutes.
So I also brought up the Eigenmodes. And this is just a kind of a quick analysis of the Eigenmodes. So there's a certain amount of noise suppression that's available. So that's what's shown here. The inset is just the noise in dB. So if you just collect the 0, 0 mode, you have this much. If you collect the Eigenmodes, you get this much. So it shows that you can get more noise suppression by collecting those Eigenmodes. And then what if you pump with those Eigenmodes instead of just the 0, 0 mode, which shows that you can get even more. So getting close to the ideal single mode case. So this is just another way to investigate how you can change the quantum properties of your beam by changing the beam parameters. And then I had one more example with heralding efficiency. So it kind of changes the focus from enhancing noise suppression into enhancing your heralding efficiency. And if you want to enhance your heralding efficiency, it means that, let's consider we have this fiber coupled experiment, and on one arm you get a click in a 0, 0 mode. You want to make sure that in the other mode you actually have a 0, 0 photon there, right? So if this is the case, you might get a click in 0, 0, so Alice gets a click, but Bob might get a 0, 0 photon, a 0, 1, 0, 2, and I actually truncated this calculation just to make it fit on the plot. So you can change beam parameters so that when you get a 0, 0 click in one arm, you get the 0, 0 click in the other arm. You boost your heralding efficiency. So I'll stop there and take any questions.
Thank you. Question? Yeah.
On an earlier slide, you had referred to a chi2 nonlinearity, but previous work was with chi3. What's the difference in spatial modes that you see between those two types of nonlinearities?
The effect with spatial modes, or what you can tailor, seems to be more dramatic with Chi3, just because typically Chi3 we're using some atomic vapor in a cell. So the cell will usually be a Rayleigh range or several Rayleigh ranges, whereas a Chi2 nonlinearity would be like very, very thin. So it's as if the Chi2 nonlinearities almost see the beam like as a plane wave, and then in the Chi3 nonlinearities, there's a chance for this entire beam interaction to go on. So whenever you predict the mode structure, you begin to see how moving the focus in one of these Chi3 nonlinearities, it's a longer cell, depending whether it's intensity squeezing or some different scheme, you can see how and predict how the mode structure changes as you move the focus around. What will the beam profile be if the focus is here? Whereas in a Chi2, you're not really going to specify that the focus is like the front edge of the crystal, the back edge of the crystal.